This is the first video of Chapter 9. We're going to talk about substitution and elimination reactions. This is going to be focusing on a specific type of compounds, which is, if you go back to the early chapters, you will find some of the function groups are basically sp3 carbon attached to a very strong electron withdrawing atom or group. Now, because of the high electron activity or strong electron withdrawing characteristic of the functional group, which will result into a very polarized bond between the carbon and this group X. Now here, the group X can be any of the halogens, hydroxy or ether, or even epoxy group, or sulfur-related groups, or even a positive charged nitrogen. Now, any of this type of either heteroatoms or groups are going to be very electron withdrawing, has a very strong electron withdrawing effect, and because of that, this polarized bond will result in a very significant partial positive charge on this carbon, the very adjacent carbon. Now, because of this significant positive charge adjacent carbon, which makes it particularly attractive to any other nucleophiles. Nucleophiles can be anything with a lone pair, anything possibly with a negative charge, will be basically attracted by this partial positive charge of carbon. Now, in this particular chapter, we're going to focus on some type of the nucleophiles or some specific type of carbons that is going to be alkyl halide. So imagine there's a halide here, and that makes this carbon particularly partial charge, and reacted with any nucleophile. There are two possibilities. One is that nucleophile will be replacing where the halide is, this X, so-called the substitution. You basically substitute one of the nucleophile, substitute the halide with the nucleophile. The other thing is possible reaction is elimination reaction. Elimination reaction is basically instead of replacing where the halide is, it's gonna remove this halide and another adjacent hydrogen. By removing this, you can form a double bond. Now, this is the opposite process of the addition we learned in Chapter 6. So a classic example would be using an alkyl halide with the chloride, bromide, or iodide as the X, and hydroxide, which obviously the oxygen has lone pairs and a negative charge. Now, in this case, we can see substitution happens. The halide will be released, and the hydroxy group will be attached to the same carbon that halide used to attach to. Now here, two very important terms or a language you can use a lot is that the hydroxide here we're using here is the nucleophile. Obviously, it's a nucleophile, and the X here, which can be one of the halides and will be released from the original structure as a negative charge, the anion, is called the leaving group. Now, leaving group is usually a group that has high electron activity and is willing to take a negative charge and leave the original structure. So basically, you clip this bond and reform another bond between this carbon and the hydroxide. Now, when it comes to this kind of substitution, it's because initiated by this nucleophile attack. So we call this kind of reaction nucleophilic substitution reactions. Now, with this kind of nucleophilic substitution reactions, there are going to be two subcategories in this reaction. And then in this video, we're going to talk about one of it, which is called SN2. The SN2 basically stands for nucleophilic substitution with a bimolecular mechanism. So what's going to happen here is we actually do the experiment to study the kinetics of this reaction. We found that the rate of the reaction is determined by both the alkyl halide and the nucleophile, in this case, which is hydroxide. So therefore, we know that the transition state of this reaction includes both alkyl halide and the hydroxide in this particular reaction. So let's take a look how this mechanism is drawn in this reaction. So when you have an alkyl halide, And let's say we know this alkyl halide has a chiral center. When the nucleophile comes in, the nucleophile will target on this carbon, which has partial positive charge, and the bromide has partial negative charge. So the lone pair will be targeting on this carbon. Now, at the same time, the leaving group leaves, which will result into a transition state. And that's going to look like this. Here the dot line means that both are partially formed and partially broken. This is the transition state. Now there are two things I need to emphasize for this particular transition state. One is that the original carbocation here, which is not a carbocation but a carbon with partial positive charge, is a sp3 carbon with tetrahedral geometry around this carbon. Now while the bromide, which is the leaving group, I have to nucleophile this. I emphasize this is a nucleophile, this is the leaving group. Leaving group is the bromide. Now, while the leaving group leaves, which means this bond is going to be broken eventually. At the same time, simultaneously, the hydroxide is going to form a new bond with this carbon. During this transition state, this carbon is going to possess a similar to sp2 carbon, which means this is going to be a perfect triangle planar geometry. Now, being said that, you probably can imagine that after the reaction, the bromide is going to be completely leave, but the stereochemistry of this carbon is going to be completely reversed. Now, the key number here is in the transition state, this is a bimolecular transition state. And that's why it's called SN2. The 2 here stands for bimolecular magnesium. Now, you probably can imagine, in this case, this carbon, center carbon, is partially attached to both the nucleophile and the leaving group at the same time in the transition state. So the space issue is going to be very big. And that's the reason why a primary or secondary halide is much better than tertiary alkyl halide in this reaction. Or in other words, tertiary halide, it does not react via SN2 magnesium at all. Let's take a look at the let's take a look at the energy diagram of this reaction. Now we start with an alkyl halide with hydroxide here, and end up having alcohol and a free halide down here as the product. The transition state is a carbon with hydroxy group on one side and the halide on the other side. Both are electron-rich group. And this transition state creates the activation edge of this reaction. And this is the only transition state, so you can see there's only one peak for this reaction, or 1 activation energy for this reaction. It's very important to remember the facts that tertiary alkyl halide does not undergo SN2 magnesium, and if there is a chiral center, the stereochemistry will be reversed. Let's take a look at a few examples of this kind of reactions. Now for each reaction, you have to be able to identify a few things. 1, what's going to be the nucleophile? 2, what's going to be the leaving group? Now the leaving group is relatively easier. Most of the time, halide will be a very good leaving group, such as iodide, chloride, and bromide. And nucleophile, on the other hand, will be something similar to this. An header atom with either lone pair or negative charge, or a carbon with a negative charge. Now, let's see if we can try to give the mechanism of these reactions. You can pause the video here, see if you can come up with a mechanism. The lone pair on the oxygen of this will be attacking to the carbon directly bound to the halide, because that's where the partial positive charge is. At the same time, the electron goes to the halide, so the halide leaves. If the reaction structure did not specify the stereochemistry, then you don't need to worry about it. The iodide will be gone as a free ion, but at the same time, this oxygen will be attached to the same carbon that iodide used to be. And make sure the remaining chain next to oxygen does not change. So there's a 3-carbon chain. The second one, the chloride is the leaving group, which obviously will be leaving with the pair of electrons. But at the same time, you can see the hydroxide, which is OH minus, with the lone pair will be coming to the carbon that is about to lose the chloride. And the rest of the structure will remain pretty much the same. On this carbon, now it's not halide anymore, it's a hydroxy group, but with the chloride. And the last one, the nucleophile is actually carbon anion, which is a carbon with a negative charge or a carbon with a lone pair. The bromide is going to be the leaving group. The leaving group leaves with a pair of electrons, which is the bond it used to have. And this pair of electrons will be coming to compensate the loss of this carbon. So this pair of electrons goes to this carbon, result into this carbon now is bonded to a triple bond. And because the triple bond is a linear geometry, so it's going to be this new bond is going to be highlighted in red, that's newly formed. I'm going to do the same with the other structure as well. I'm going to highlight the bond that's being formed. At the same time, it's going to have a free bromide.